trouble with this is that if you have a new sort of technique or a new type of memory error, well then your results will fall apart, and certain of the techniques that the compilers use to break certain memory errors can be circumvented. So other approaches are randomization approaches, things like address space layout randomization, which is where you move around the stack and the heap and things like that, so that once the attacker adds his malicious code, he has no idea where it is. And if he doesn't know where it is, then he doesn't know where to point the instruction pointer. But things like this are also circumventable, and they also tend to have low entropy, so that an attacker might be able to guess. So for example, a few years ago, there was this exploit for Windows to do the animated cursors. It was a really strange little exploit. But after that came out, I went on Google, searched for the exploits, and the very first one that popped up said, vulnerability exploit, Microsoft ANI cursor bypasses address space layout randomization. So what that tells me is that this is possible to get around, so it might not be a good fix. Instruction set randomization is another randomization approach, and the thought here is just encrypt all the code, and then the attacker doesn't know the key, so he can't create new code. The problem is you have to decrypt all that code at runtime, which causes a performance penalty. Now, kind of the main approaches that seem to be the most effective tend to be the architectural approaches. And the main one in that is called the NXBit. PAX is a software version of the NXBit. So the NXBit is basically a hardware change that both Intel and AMD have made to take a whole page of memory and to say this is not executable. So now if the attacker adds his code to this page, then he won't be able to execute it. But these two tend to be circumvented by attackers. So we have a set of existing work, but it's not fully sufficient. So what role or how do I envision this new architecture working? Well, I made a really important claim, and I said that this architecture has to work without making any hardware changes. And yet I'm still saying that I need the processor to be able to be split across these memory spaces and have that enforced. And that's possible on Intel or AMD x86 systems by making creative use of the TLB, which is the translation look-aside buffer, and the page tables. So the TLB is a little teeny hardware cache that caches page table entries for virtual memory. By using this creative work, I can make sure that data accesses go to one portion of memory and instruction accesses go to another. So let me describe that for you. In order to illustrate it, I want to show you two quick overviews of operating systems. The first is how to handle a page fault, and the second is going to be how I've modified the general page fault algorithm to accommodate this new architecture. So if you've taken an operating systems course, you're probably familiar with a page fault, but I just want to show you virtual memory and page faults on the Intel system. So imagine that we have logical memory, and we have our 5 logical memory pages, 0 through 4. And let's say that a program is running, and it makes an access on logical page 1. Well, what that'll cause is the hardware, when it's trying to translate that to the physical frame that it corresponds to, will check the translation look-aside buffer to see if there's an entry available for logical page 1. If there's not, then that's called a TLB miss, and the hardware will then go to the page table to see if the page table has information about that mapping. If the page table doesn't have any information about that mapping, then the hardware gives up, and it signals a page fault, which is its way of telling the operating system, you're trying to make a memory access that I don't know how to do, you better fix something. So the operating system will then go to its physical memory map and will pick out a free physical frame, in this case frame 7. It'll also check its backing store, maybe the disk, to see if that page used to be in memory but was swapped out to disk to make space for something else. If it was, then it'll bring that page back in, and then most importantly, it'll update the page table to reflect that now there's a physical page backing that logical one. And at that point it restarts the instruction. When the instruction restarts, we go back up to step 1 again, where the hardware checks the TLB, doesn't find an entry, then goes to the page table where it does now, it fills in the TLB, and it runs that instruction again at full speed. And any future accesses to that logical frame will actually go full speed because the TLB entry will be used to provide that mapping. So, how do I change the page fault algorithm so that we can have this new architecture that enforces a split between code and data? Well, in that last description, I actually told you a very small fib. And that fib is that I said that the machine has a TLB. And that's actually not true. Modern machines actually have 2 TLBs, one for instructions and one for data. And the reason for this is because they're limited in size as to how many entries these TLBs can cache, and instructions and data have drastically different usage patterns. Instructions tend to be very sequential, data tends to be more random. So to keep performance up, they have 2 TLBs so that random data accesses don't end up evicting instruction entries from that. But we can use this to our advantage. So this is what modern hardware has. Let's imagine for a moment, in a theoretical world, that it also had 2 page tables. So we had a code page table and a data page table. and the two were separated. Now these two page tables are identical except for one entry. The entry for logical page 1 in the code page table goes to physical frame 6, and in the data page table goes to physical frame 7. So that means that if we were to have these two page tables, that an instruction fetch off of that logical page would go to a different physical page than a data read or write. Now this is exactly what we're going for in trying to construct this new architecture. Instruction fetches go to one portion of memory, data reads and writes go to another. So if we could have a system like this with two TLBs and two page tables, we'd be all set. But sadly, the actual Intel machine does not have two page tables, it only has one. But what if we kept that page table invalid all the time? So whenever a TLB miss happened, the hardware would run to the page table and find nothing. So at that point it would initiate a page fault. Now, I've made the page fault handler more intelligent. So the page fault handler is able to take that page fault and determine whether it was for a code access or a data read or write. If it's for a code access, then what it does is it goes to the code page table and it copies that entry down to the normal page table, and then it causes the hardware to initiate a fill of the TLB off of that page table, so that entry gets cached in the TLB, and then it invalidates the page table and restarts the instruction. Now the page table may be invalid, but if there's an entry in the TLB, then the memory access will succeed and the instruction will be able to run. And I can do the same thing for the data page table, moving those entries down and causing the hardware to load those into the data TLB. So at this point, the instruction TLB and the data TLB can be desynchronized, which means that your accesses for one particular virtual address will actually go to different physical pages, which is perfect. This is exactly what we want to have happen for our new architecture. So that's how we build this architecture in the operating system for the user level. Now there's two kind of deeply technical points that I just want to illustrate real quick about how I fill that TLB. Don't worry if you get totally lost on these two slides. They're not important for the overall vision. So how do I fill this data TLB? Well, there's actually an operation called a page table walk that I do. It's fairly simple. Within the page fault handler, I make that page table entry valid by copying the entry from the data page table, and then I touch the memory address that faulted. That causes the hardware to fill in the TLB just like I want, and then I invalidate the page table entry, and I restart the instruction, and everything continues as you would expect. To fill the code TLB, though, it's a bit more complicated. I don't have anything nice and easy like a page table walk. So I use a single stepping mode in the processor. Single stepping mode is a mode that you can set so that the processor will run one assembly instruction and then throw an interrupt for the operating system to intercede. So what I do is I make the page table entry valid by grabbing the entry from the code page table. I enable single step mode, and then I restart the instruction that faulted. So now that one instruction will run, that'll cause the instruction TLB to be filled, and then I can catch that single step interrupt, invalidate the page table entry, disable single step mode, and let the system continue to run at full speed. So how effective is this? I really ran two different types of tests. One was a benchmark test called the Weilander benchmark. And what I really want you to gather from this slide is that the Weilander benchmark was one that was designed to show all the different ways that an attacker can hijack that instruction pointer and get it to point to his injected code. But since our approach works by simply preventing him from ever executing injected code, it's able to handle all of the tests without any trouble. Now, probably the more interesting effectiveness test is on real-world vulnerabilities. So I went back and I grabbed 5 vulnerabilities from 2001 to 2003, things that covered web servers like Apache, FTP daemons, Samba, a DNS server, stuff like that, and that had a variety of different corruptible memory regions. And the goal here is to see how well does the system perform on real-world attacks, and it was able to stop them all without any trouble. Now performance. Performance is always the most important part of any sort of implementation like this. So I ran 4 different benchmarks. One was I tested the throughput of Apache, so how many pages it could serve up per minute. I tested how long it would take gzip to compress a large file, and then Unixbench and Nbench are both benchmarking programs for systems. So the way to read this chart is the blue box represents an unmodified system. So it runs at what I call 100% speed. And then the purple box is the percentage of full speed that my modified user level system can run at. So my performance is above 80% in all these cases, and I consider these to be a good overall basis, or a good overall way to demonstrate the performance of the system. But I also want to show you the worst case performance of the system, because it kind of illustrates one of the main weaknesses that this approach has. So this is kind of a more zoomed in graph on how Apache, that throughput test worked. And what I found is that when I tested the throughput of Apache with very, very small pages, my performance dropped like a rock, so a little below 50%.